welcome back. Please settle down as soon as possible. Starting now. So this will be the second last chapter in this year. After superposition, there's another one on parametric theory. Yay!
Yes, absolutely.
Regarding feedback on the whole paper, right, you will receive the feedback by email. So we need to learn it for the Okay, so we're going to start with the first lecture on superposition. I sent an email to all of you yesterday. So this will be the first lecture. The second lecture will be next week, Friday. And the last lecture will be on week 10, which is during your lecture day. Very noisy, I already started. When I say very noisy, some of you are still looking at me. Do I have to point at you? But this is not an easy topic because it's something that you might not observe every day. Okay, so you need to use some of your imagination. In this chapter, we are going to look at, continue from the previous topic, we talk about waves, right? So in this chapter, we will look at what happens when two or more waves overlap. For the A-level syllabus, we are only looking at two waves. Two of them. You can have 3, 4 or more waves overlapping. Okay, so for the A-level syllabus, you are only doing 2 waves. So as you can see on the screen now, those are coming in, can you settle down? And this one, you can see that the 2 waves, right, they actually meet and they overlap and they produce the resultant wave. So that is called superposition of 2 waves. Similarly, this one here, also superposition of the 2 waves. So we will see later how the wave is formed, the resultant wave is formed. But before that, let me bring you back to what you have learned previously. We learned that light, which is a wave, is traveling in a straight line. Okay, so how do we then represent the light wave? We use ray diagrams. So you draw lines, and then what you are doing is actually by geometry. So this is called geometry optics. But now we are not doing ray diagram anymore, because ray diagram is not sufficient to explain the observations that we are going to make. Now what we'll be using, if you turn to page 2 of your lecture notes, we will be using sinusoidal curves. Those are sine wave, cosine waves. Sometimes we also use wavefronts. So you need to be very familiar with these two ways of representing waves. So sinusoidal waves are a problem. This is a sine and cosine wave. So as you can see here, you see, so this is how you draw the wave. The one in green arrow, this is the direction of the wave. So what are wavefronts? They are imaginary lines. Okay, they're not there, but they are actually lines that join points that have the same phase. Okay, if you recall, in SHM, as well as other waves, we talk about phase. What do you mean by phase? Okay, phase is a state of disturbance. This is a relation. And how do we measure phase? We use angle. Okay, so if they are all at the maximum displacement, if you imagine a circle, they will be at the same point of the circle. So we say they have the same angle, therefore they are having the same phase. So a wavefront is a line that joins all the points that have the same phase together. So this is a wavefront. You can see another wavefront here. They are joining all the crests together. So this is one wavefront and the next wavefront. The distance between the wavefronts will be exactly 1 wavelength. This is always true. Similarly, I can also draw a wavefront whereby I join equilibrium, all the points at equilibrium. Then the next wavefront will be here, and so on and so on. But by default, if it's not mentioned, wavefronts will be line that join all the crests together. Okay, so the point is just now, ray diagram is not enough. Why? Because we cannot explain what we see in this picture. Can you see in this picture there is this water waves here? They actually encounter obstacle, the rocks here, there's a gap in between, and then what you see, the waves start to spread. Do you see these patterns? These are called equilibrium patterns. So if you draw a ray diagram, there's no way you can explain this. So we need to use sine cosine graph or wavefronts. What you see here are actually circular wavefronts to explain the spreading. So the waves spread out, and the pattern is called interference. So this is what this chapter is all about. We'll be using superposition to explain spreading, diffraction, as well as the pattern that you form, interference of waves. Okay, so to start off with, let me tell you in this chapter a lot of definitions, a lot. All those important definitions I already highlighted to you, they are inside the box. So all those must be memorized. Just to share with you, I don't have the question here, but if you have a TYS, one of the year, maybe more than 1 year, the question on superposition is just defined, and they give like 7 or 8 terms with this superposition. And so it's very important that you know the meaning of the terms. This is the first one, okay, which is principle of superposition. Many of you are not very good at that, especially, you know, we test you so many times, definition is still got it wrong. One of momentum. So seriously, I would advise you to have a notebook. Write down all the definition of the terms, as well as all the concepts. It's good when you want to be honest. Okay, let's come back to here. What is the principle of superposition? Those highlighted in yellow, very important. Well, it refers to, or rather it states that the resultant wave displacement. Okay, that is the total displacement. If you are referring to the maximum displacement, then the amplitude. Okay, so the total displacement or the total amplitude is given by the vectorial sum. Okay, very important that is the vectorial sum. Okay, not the algebraic sum. Algebraic sum, that means you don't care direction. Vectorial means you care about the direction of the individual wave displacement or amplitude at the point where the waves meet. Okay, so if you look at the first diagram here, constructive interference, can you see that the two waves they are having a positive displacement? So it's all in the positive region. So what you do? You take the sum. Since they're in the same direction, you just add. Okay, so if one of them has a displacement of say 0.75, the other one is 1, total displacement 1.75. So that is the vectorial sum. Then on the other side, you can see that these two waves, they are in the opposite direction. So what do you do? Vector. Opposite direction, you subtract. There you go. How about any other direction? So far, we don't test you any other direction, but I don't know whether it will come out. So if it's any other direction at angle 45, what do? You resolve and you add. Okay, but so far it's same direction and opposite direction. It's already enough. Okay. So bear in mind, highlighted here, you must take the vectorial sum. Similarly, when you are asked to state the definition and we didn't say it's the vectorial sum, definition is wrong. And I want to highlight that the waves that you add, you can only add waves if they are of the same type. If I have water waves, I cannot say water wave superimpose with sound wave. How to add? Cannot. Okay, so if it's interference of wave, it must be sound wave and sound wave is superimposed. Water wave and water wave, and so far, they must be of the same type. Okay, so different type cannot superimpose. So we have an example here. This is a warm-up exercise to apply the principle of superposition. So I'll give you some time, 2 minutes, read the question and try. Okay, you are supposed to sketch the resultant wave using the principle of superposition. Same direction you add, different direction you subtract. Okay, that's the answer for the first one. You need to calculate the distance traveled by the pulses. And then you realize that, hey, actually they haven't meet, they haven't overlapped. So the resultant just looks like this. Okay, then you do the same thing when t equals 15 milliseconds. Draw the individual pulses first. The answer for the second one is just a straight horizontal line because they overlap and they cancel out according to the principle of superposition. So you should end up with 0 everywhere. Okay, so very easily done. Apply the principle of superposition, but before that you need to know what is the exact location at a given time. Okay, so you need to draw the individual pulses and then you apply the principle of superposition. So that will be the answer for all three. So in the same direction you add, in the opposite direction you subtract. Okay, so with that we are done with the example 1. Can I move on? Okay, this part is very important and you do not understand and you are lost. Please ask your friend to explain to you how to get an understanding. Because if you are lost here, you will be lost for the rest of the lecture itself. There is a part B to this question.
what has happened to the energy at t equals to 15 milliseconds. If you look at the second graph, it's a straight horizontal line. It looks like there's no wave. So what happened to the energy? Where is it now? It is not zero because it violates the law of conservation of energy. So where's the energy? Well, the energy is still inside the wave. It's trapped within the wave, just that you can't see it at that moment. The next instant, you see the pulses back, so the energy comes back. But at that instant, when t equals 15 milliseconds, it's trapped within the wave. Only at that time. Trapped is stored inside. It is like now it's at an equilibrium, but it doesn't mean that there's no energy. The energy is there within the particles. So the particles have kinetic energies. So it's stored inside as kinetic energy. Okay, I'm going to move on to reflection of wave. Still on page 3 of your lecture notes. Can I move on? Okay, so for reflection of wave, you need to be very careful. There are two types of ends that we are looking at. If the end is a fixed end, for example, you have a string, and then you tie a string to a support. Okay, so that is a fixed end. So what happens when you have a pulse, okay, that is traveling towards the fixed end? Oh, this is the loose end. Okay, so if you have a pulse with a positive displacement, when it goes to the fixed end, there will be 180 reflection. So we say that there's a phase change of pi, or 180. So why is it like that? It is because of Newton's third law. When the wave particle actually exerts a force on the support, it will be outward force. Because the pulse is a positive pulse, so the force will be pulling the support up. Then according to Newton's third law, the support will exert a force downward on the pulse, therefore the pulse gets reflected. So this is what happens when a wave encounters a fixed end. What happens if it's a loose end? If it's a loose end, that means it's free to oscillate. Okay, so if it's a crest that is coming in, it will still be a crest that is going out. Okay, so there won't be any reflection. So as you can see here. So we are done with the principle of superposition. Yes and not quite, because the rest of the sections, right, we'll be talking about how we use principle of superposition to explain the different types of waves that you see. So the first application here that we are talking about will be the formation of a standing wave. And to bring you through the formation of a standing wave, I'll be using an applet. Okay, this is a very useful applet. In fact, for e-learning, I'll be using this applet. Then everybody have to go to this applet in order to answer the question. Okay, where do you find the applet? At the end of page 4, I actually give you the link. So you can actually go back and try. Okay, so let me show you how it looks like. It will be good that you actually play with it. I'm going to show you, okay, how a standing wave is formed. Okay, you need to look carefully because later I'm going to ask you how a standing wave is formed. Firstly, we have to select the reflection. This is the end. I can choose a fixed end or I can do a free end. So I'm going to choose a fixed end. That means when the wave, right, when it encounters this fixed end, it will undergo a reflection, 180 degree reflection. And okay, we are going to see incident, reflected, as well as the resultant waveform. So we're going to start the animation. So there is a wave coming in. This one is purposely slowed down so you can see the wave. The black dots that you see are the particles in radius. It could be a string. So you can see that when I send the energy, the particles are being displaced. How do you describe the motion of the particles here? Up, down. So what kind of motion is that? Simple harmonic motion. So this topic is really very simple. See what happens when the blue wave is the reflected wave. What about the black one? Resultant. What is the resultant?
and subtract accordingly. So you use the principle of superposition. Can you hear me without the mic? Goes at the back. Can? Okay. Okay, wait. I still need the mic. So as you can see here, a resultant wave is not formed immediately. Okay, but most of the time, because the speed of sound, speed of light is so fast, to us it's immediate. So this one is purposely slowed down so that you can see. To form a standing wave, you actually need an incoming wave overlap with another wave that is traveling in the opposite direction. And the wave must be identical. Okay, so that they have the same amplitude, same frequency. So how I did it here is I send an incident wave to a fixed end and then it gets reflected, right? So the two waves are identical, assuming there's no energy loss. So the red wave that you see, that is the incident wave, and the blue wave that you see is the reflected wave. The black one is the resultant wave. If you refer to your lecture notes, can you take a look at the lecture notes, figure 4. Okay, this is similar to what you see in figure 4. Okay, right now what I've done is I actually stop the animation and I do it in single steps of t/4. Okay, so the next, if I click next, right, resume, what you will see will be time t/4 seconds later. Okay, where t is the period. So at this instant, this is similar to your figure 4, which is at t equals 0. You can see that the incident wave, which is the red wave, overlap exactly with the reflected wave, the blue wave. So they look as if like they are one. If you refer to your lecture notes, right, the incident and reflected wave, I represent them using a dotted curve. Okay, so the two curves are identical. So in fact, that dotted curve consists of incident curve as well as the reflected curve. Okay, so when I apply the principle of superposition, at this point here, you can see this point, the resultant displacement will be 2 times the individual amplitude. Okay, so the result, if this is A, the resultant displacement here will be 2A. So if I ask you to sketch for me the standing wave, your answer will be just this. No need the incident and the reflected wave. So this is how the standing wave look like at t equals to 0. Okay, I'm going to do the next step, which is your figure 5. So that is 1/4 t later. The resultant wave look like this. So this is how the standing wave look like. Why is it look like that? Let's take a look at the reflected wave as well as the incident wave. They are exactly out of phase. That means the crest, if you look at this part here, the crest of the red wave actually meet the trough of the reflected wave. So if I use vector addition, the resultant will be 0. Okay, so at any other point, you see that any other positions, the resultant will be 0. That is why the resultant wave is just a straight line. Okay, so that is your figure 5. Then, if I were to go to the next step, that will be half a period later. Okay, the resultant wave, which is the standing wave, will look like this, figure 6. Why? Because, again, if you look at the incident and reflected wave, they are reflected wave, they are in phase. So when the resultant amplitude is the maximum like this, we call this constructive interference. So if you look at your lecture notes, figure 4 and figure 6 both are constructive interference because the resultant waveform is larger, having a larger amplitude than the individual waveform. Okay, then if you look at figure 5 and figure 7, okay, figure 7 will be next step. It will look like this. You will find that the resultant waveform is 0. Why? Because they cancel, right? Using the principle of superposition. So this is called destructive interference. I'll be talking more about constructive and destructive interference in your last lecture. Okay, so for the time being, you just need to know that constructive interference is when the resultant amplitude of the wave is larger than the individual. Okay, destructive will be when the resultant amplitude is less than the individual. So in this case, they totally cancel out. So that is destructive interference.
Okay, then I'm going to resume the animation. Now I want everybody to look carefully at this point. Is the cursor there? Yeah. Okay, can you see this point, which is the fixed end? What can you say about the resultant displacement at that fixed end? It is always zero. Always. There's never a time whereby it gets displaced. So there's a name given to this point. We call it a node. N-O-D-E. Okay, that you can find on page 5. I highlighted again. You need to know how to define a node. A node is defined as a point at which the displacement is permanently zero. Similarly, if you see this point here, the displacement, the resultant, which is the black wave, the resultant displacement is always zero. Although the incident wave and the reflected wave, they have different displacement, right, at that position, but when you add them up, it is always zero. Similarly, here, the resultant is always zero, and so far, so on. So can you see that the nodes, right, all these nodes here, adjacent nodes are exactly half a lambda apart. Okay? Then at this position, okay, where my cursor is, what do you notice about the displacement? Compare the particles here compared to other particles nearby, the neighboring particles. At any time, the displacement is always the maximum. Can you see that? Okay, this particle that is in the middle, at any point, any time, the displacement is always the maximum. So we call this an antinode. Okay, so as you can see, antinode is defined as a point with the maximum amplitude. But the amplitude of that point is not always at max. It varies between maximum and then decreases to zero, and then the other direction, maximum, and then go back to zero again. Okay, so antinode doesn't mean that the amplitude is always, or the displacement is always at the amplitude position. No, it changes from maximum to minimum, then to negative, and then come back again. But the amplitude is maximum at that point, compared to the others. Okay, I'm going to select another point. Is it better I use this one? Okay, if you look at this point here, you can just see this point is being displaced, but the amplitude of this point, the maximum displacement, is always less than the one at the antinode. Okay, at any time it's always less, except at equilibrium, they are all zero. So that is why this point here is known as an antinode. What can you say about the distance between successive node and antinode? In terms of lambda. 1/4 lambda. Okay, so these are the characteristics of the standing wave. Okay, so with that we are done with the formation of the standing wave by applying the principle of superposition. There is a checkpoint that I would like you to look at it now. Oh, before the checkpoint, okay, I'm going to ask this question. How is a standing wave formed? I want you to turn the person sitting next to you. Take turns to explain. How is a standing wave formed? Okay, you have 1 minute. If you are not talking, I will bring the mic to you. How is a standing wave formed? important features are how a standing wave is formed. But I hear collision. This is not particle-particle collision. So two waves they don't collide. What happens when two waves meet? No collision, but they overlap or superimpose or they interfere. You must use the correct term. Okay, so how is a standing wave formed? Well, as seen in the applet just now, a standing wave is formed only when you have two waves. If you only have one wave, there's no standing wave. Okay, you need two waves of the same speed, same wavelength, same amplitude, and of course same type. Okay, they must overlap and they must be traveling in opposite direction. Okay, so all these conditions must be met, then you get a standing wave. One of the past A-level exam questions, how is a standing wave formed? So this is the answer.
Okay, so with that, we are ready to move on. Checkpoint on page 5. The definition can be found on page 4, highlighted in the box for you, the first box. Can you see that? How is a standing wave formed? A standing or stationary wave is formed, blah blah blah. So that is exactly the same as what you have on the screen here. Okay, page 4 at the top is boxed out for you, so that one is important. So when they ask how is a standing wave formed, this is the answer that you will give. Okay, with that we'll move on to checkpoint 1 on page 5. On figure 4 to 7, label all positions of nodes and antinodes. Okay, 4 to 7 too many. Can you just do figure 4 and 5? Okay, I give you 1 minute, you do that now. Okay, just figure 4 and 5. If you want to do the remaining one, you do as well.
What happened next? So if it's going to display, it's not going to be a node. So the position of the node will never change.
So if you look at this animation again, it's labeled in the animation the position of the nodes and antinodes. So if you look at here, and the fixed end is always a node. The displacement is always 0. So t equals 0, t equals quarter t, half t, and so forth, so on is always 0. At this point, this is always antinodes. Why? Because the displacement is always maximum, the amplitude is always maximum compared to the neighboring particles. Okay, similarly this point is always a node. So whether you are drawing at t0, t equals to a quarter period, the positions of the node and antinode never change unless you are referring to a different standing wave. Okay, so your answer for figure 4 and 5 must be the same. similarly, if you are doing 6 and 7, they must all be the same as well. Okay, so with that, I'm done with this section. Let's move on. We're going to look at the characteristic of standing wave. If the wave is not standing, what type of wave is that? Huh? If it's not stationary, why is it that we call... Very noisy. Jumping wave. Okay, why is it that we call this wave stationary? If you look at the resultant wave, is it moving to the left? Is it moving to the right? No, it is just staying there. Okay, so that's why it's stationary or standing wave. So if the wave is not standing, what do you call that? You learned that before. What do you call it? Something that starts with P. Progressive wave. That's right. Okay, progressive wave is what you learned in the previous chapter, right? And you learned about characteristics. So, very noisy. How many characteristics do you learn for progressive wave? You mean, very good, 6. Okay, there are 6 characteristics. So similarly, in standing wave, there are also 6 characteristics we are looking at. And I call it field pole. Okay, what are the 6 characteristics? You just need to remember field pole. Okay, what is field pole? Over here, you see a standing wave, and the curve that you see, right? Okay. The curves that you see here are at different timing. Okay, this could be at t equals 0, then sometime later, this is a standing wave, sometime later the standing wave, and so on so on. So these are at different timing. The one that is going up and down is the standing wave that you actually is seeing at that instant. So the first characteristic, what we do see is that the frequency of the oscillations of all the particles, they are all the same. Okay, frequency will be the number of oscillations, right, in 1 second, which is related to the period, frequency over t. So if you were to look at this particle, the time that it takes to go down to the lowest place and the highest place is the same as the neighboring particle. So the time taken for them to complete one oscillation, they are all the same. If they have the same period, they have the same frequency. So they take the same time to go to the maximum, all maximum at the same time, equilibrium and lowest point at the same time. So they all have the same frequency, except at the nodes because it's not moving. Okay, next characteristic, so this is F. E. E stands for energy. There's no transmission of energy. Because the wave is not moving forward, neither is it moving backward. So the energy is just trapped within the wave. So it's inside there. Okay, but it's not moving forward. So there's no transmission of energy. Next characteristic, this is something that we see just now. Wavelength. The wavelength will be exactly the distance between 2 successive nodes or 2 successive energy nodes. We are all summarized in the table for you, so you can refer to the table. The next characteristic is the phase. Remember we say the phase, right, is described by the angle. So particles in the same loop, they all have the same phase. Why? Can you see that at this instant of time, all the particles have maximum displacement? You can imagine they are all at the top of the circle. But the radius of the circle are all different, but they are all at the top. So the angles are all the same. Then the next instant, when they go to equilibrium, again the position of the circle will be all the same. The angle that they cover will be pi over 2, 90 degrees. So they all have the same phase. At the lowest point, compared to the highest point, the phase will be 180 degrees. So all of them are having 180 degree angle. So they are all having the same phase. So particles in the same loop or same segment, okay, defined by the 2 nodes here. So this is one loop or one segment. They all go up together, come down together. So the angle, right, the position in the circle are all the same. So they are considered in phase. What about particles in adjacent loop or alternate loop? If you look at the particle here and the particle here, when this side of the particle they are going up, the other side is going down. Okay, so if one is up, one is down, they are exactly out of phase. So we say that there is a phase difference of 180. So that is a characteristic. Only
seen in standing wave. For progressive wave, there's a formula, right? Different point has different phase. So you need to calculate using that formula, which is introduced in the previous chapter. So I've given you that in the table. Okay, what about the amplitude? For progressive wave, every point will have the same amplitude eventually. But standing wave is different, the amplitude varies. At note, amplitude is 0. At this point here, need to note the amplitude is only like 2.5 boxes, 2.5 units. That's the maximum displacement. Next particle in a higher amplitude, when you see that? The maximum displacement, and so on, so on. Maximum will be when it's at antinode. So different particles have different amplitude. So this is different from progressive wave. And finally, the last characteristic, the wave profile. The standing wave, because why the wave is not moving. So the wave profile does not have lines. Well, so when I'm done with the 6 characteristics, here is a Hall. This now is a wave. Okay, the question. So, A-level question asks is, what is a standing wave? So again, I want you to turn the person sitting next to you. What is a standing wave? Misconception in the exam. Many students, when they are asked how or what is a standing wave, they are asked what is a standing wave. They write down a standing wave is formed when 2 waves overlap. Can or not? Are you answering the question? No, the question is not asking you how a standing wave is formed. The question is asking you what is a standing wave. So you need to give the characteristics. Okay, so that is the second box that you see in your lecture notes. You know how a standing wave is formed. So maybe I'd like to encourage you, can you turn to your lecture notes? What page is that? Page 4, right? Page 4. The first box is what is a standing wave? The second box, the first box is how is a standing wave formed? The second one, answer the question, what is a standing wave? So if you are asked what is a standing wave, well, it is one that whereby the wave profile does not travel in the direction of the wave. Okay, the particles are still oscillating, and then there's no transfer of energy. This part you can write a lot because there are 6 characteristics, right? So usually we describe the term of wave profile, as you see here, as well as energy transmission. But if you are given more marks, then you write more characteristics. Okay, next. I'm going to the next section, which is your page 7. There are 2 categories of stationary waves, just like progressive waves. There are 2 categories. So one is transverse, the other is longitudinal. Okay, right here, very noisy. You all know what is this? Have you all played with this before? What is this? String. Slinky. Okay, this one is actually slinky. We can use this slinky to show the formation of the standing waves.
for both longitudinal as well as stationary. Okay, so this is a challenge, so later I'll invite some of you to come down. But before that, let me explain to you. In longitudinal wave, progressive wave, right? We say that the direction of the vibration is the same as the direction of the wave. What about a longitudinal standing wave? So you can say that now the vibration, okay, the wave travels this way, let's say from left to right. You notice that the vibration is in the same direction. But what you notice that is different in standing wave is that there is a position whereby the particles will not slip. It stays stationary. Okay? Then at other position it oscillates a lot. This one the amplitude not as much. This one will be the antidote because the displacement is the maximum. Okay? And then this one not moving, and so on, so on. Traverse wave is what you see just now in the applet. So right now, anyone would like to come down and try? How do you actually use this pinky to show the formation of a standing wave? Anyone? The prize is you get a slip. Whether they want to demonstrate longitudinal standing wave or traverse standing wave. Choose one. Or maybe you can do the same.
I am Donovan from International.
So which one will you
Because
This one's
Oi, corner, oi, come on.
Because gravity, right? So it's making, there's a weight, so it's being pulled down. I'm not so far, don't never see that. So that's the stage here. You don't see the standing wave? The frequency has to be correct. If you do it too fast, you find that the standing wave is gone. If you slow down, the standing wave is really gone. If you do up and down, standing wave is also gone. Remember, converse, this is the direction of the wave. One person will be standing the wave. The other end, let's do a fixed end. Who is the fixed end here?
Corner.
Do you see the fixed end?
Corner.
You do, right? And then, you change your frequency. So you see your standing wave is gone. It must be of the correct frequency. Is it okay?
Very tiring.
Very tiring. Can you see in the middle, the point, it's not so good, but it appears it's like it's not moving. So that is where the, what is that? We got it? In the middle now, okay, later.
Wait, do you get it?
Yeah, later. I give you a better one. Because now do you see standing wave? I didn't do it gently. As you can see just now, when one end is fixed, right, the other end is doing the transmission of energy. There's a point in the middle whereby it appears to be stable, but not quite. Because why? We need scale. We You need to be at the right frequency, and you need to maintain that frequency. Then you can get a note from a denominator. So at the two ends also you should see a note. Then somewhere in the middle you see, what do you say? C and D. So how do you all think they've done it? Fail or success? Fail? Not too bad lah, okay? At least when you don't see standing wave. How about longitudinal? Anyone want to try? Anyone? Longitudinal? Anyone on this one? You know time is running out. And then I will get one person to help me hold. Let's hold. Okay, if it's longitudinal, how do you oscillate? Okay, now? So if I will do it here, in the middle. I'll do it on the table, but not in the middle. You see that the color in the middle is the green, it is not moving. The rest are this one is already out of shape. The pie is a smaller one. This is the bigger one for Daniel. Do you have a pen? Come and write down your name. I'll pass it to you.
Don't get pen, don't get pen. Oh, thanks.
Hey, can you write smaller? Oh my god, I have one whole page. Can you write smaller, please? In your class? Your class? Sorry? How does it apply? It's the same here. At this instant you can't see them. So you got to wait for your they will just show you. So you don't have. If here I can't tell. Okay. I need to see the whole wave. Or at least half period. Then I can tell where the notes and what the notes are.